last-minute thing, but will stick with us for the balance of the semester. Okay, so it's good to see you folks again. This afternoon we're going to be going into material that is going to follow us through much of the terms about commonalities among dynamic modeling methods and about some of the distinctions between those methods. Just as a reminder of what we talked about last time, I noted last time that in dealing with phenomena in the world and trying to understand and more importantly make decisions about factors in the world, we're often confronted with what are called systems problems or complex problems. Complex is described as a term. It's described in many different ways. Some people use it as a synonym for complicated, but I actually mean something quite different here. I mean something quite specific with respect to the notion of a systems phenomenon. What I'm referring to is a phenomenon where the whole cannot be reduced merely to the sum of the parts. We actually see behavior, we see dynamics, as it's called, that is activity over time, which is distinctive for the system as a whole compared to the individual pieces. By and large, science has been exceptionally successful and productive in explaining how things work by taking them apart, by successively studying the smaller pieces. So you think about the enterprise of biology, you think about chemistry, you think about physics, elucidating particular mechanisms underlying aspects of human medical condition, etc. But one of the big insights from the past 100 years or so, particularly from the past 50 years, is that taking things apart, studying the pieces in isolation, is only part of the picture. It's a key part of the picture to understand how things operate, but it only provides half the story. The other half of the story is how those pieces and their connection to each other give rise to the overall behavior we see. And whether it's the Human Genome Project or aspects of biologic functioning or the sphere of competition between companies or large-scale health issues, increasingly people have realized that the shortage of our understanding is often most acute, not about the pieces, but about why the system behaves as a whole the way it does from those pieces. So it's not about understanding the pieces where we have our shortcomings. It's actually about how those pieces combine to yield the overall observed behavior. And I argued that there are a number of phenomena that you folks may be dealing with over the course of your careers where this really applies. An example that I sort of trotted out informally was the example of a traffic jam. I argued that if we wanted to solve the problems of traffic jams by the University Bridge within this city in the most effective way, we'd have a hard time doing so by just studying how cars work in isolation, studying the axle sizes prevalent in Saskatoon, the types of chassis seen, the types of engines which are within cars. There's something about a traffic jam that transcends, that's more than simply about the vehicles. It's not that vehicles have nothing to do with it. After all, a slow vehicle can lead to quite a backup, but that's not all of the picture. Nor is it merely a matter of the road and its curvature and how wide it is. Surely that has something to do with it. If University Bridge was served by a 10-lane thoroughfare like they have in Southern California, it might be a little bit different for crossing the bridge. But that's not it either. Even those 10-lane thoroughfares in California, they have terrible, terrible traffic jams because of other bottlenecks. So it's not that the pieces are irrelevant. It's how they come together to yield the overall behavior that's important. And traffic jams are about combinations of psychology, yes, about the shape of the road, yes, about the nature of the vehicles involved, but also about the network of other roads coming together. It's not any one of those things in isolation. It's the combination of all of them in a complex way. And just like doubling the size of the bridge over to the west side of the city wouldn't have the size of that traffic jam. So it is with a lot of situations that we have these kind of nonlinear effects. We lack good intuition about how if we change this, how other things will change, how the behavior as a whole. So traffic jams are just one example of this. For those working in the computer science or computer engineering field, there's lots and lots of other examples. Performance scaling behavior of a system. You could have a set of computer clusters and fast machines, and you need to think about it as a whole, because if you go and you double the speed of that network, you won't necessarily double the speed of the cluster. It may be that the real bottleneck is how jobs are handed out to the different computers and their CPUs. Or maybe the bottleneck is the memory involved. And you could up the CPU speed, to a very, very high level. You could double the network bandwidth, and you see very little speed up because it's memory constrained. We have different ways of talking about these things, but in these cases, we're talking about systems level phenomena. Cases where the whole is greater than the sum of the parts. The performance of that whole computer system is not merely reducible to the particular aspects of the CPUs involved, or the particular aspects of the network. It's a complex combination of those that give rise to it. Not complex in the sense it's inherently opaque, but complex in the sense that there's behavior that arises that transcends any one of those pieces. And we see situations like this throughout nature and throughout human systems, whether it's in competitions between companies or arms races between countries, whether it's spread of memes and rumors over social networks, or circulation of infections in a population. We have these kind of systems level phenomena, these complex systems where we need to reason about them to do a good job. And I introduced this notion of emergence last time when we were running that little simulation model. That simulation model where we posited a very simple theory of personhood, and we asked, what is the consequence logically of that theory over time? And we saw some sort of behavior there that was not in any way pre-programmed into the model, not in any direct sense. It was these concentric rings. And we saw that slight modifications of our assumptions, like introducing a situation where people could go back from being recovered to being susceptible, could lead to big differences in this emergent behavior. And we could have searched through that model, in and out, looking for where those rings were specified in the model. Where do we specify that there's a ring? Where do we specify that the susceptibles will be outside the infected? So we would never find it, because it's not explicit, it's implicit. It results from the interactions of things. It's emergent, in short, ladies and gentlemen. And the patterns that we see are quite different from what you'd expect from any single component of that system. They relate to the variables in the underlying system in complex ways. Now, why is this an issue? Well, one issue is, ladies and gentlemen, often in the world, we need to provide an explanation for patterns that we see. Those of you who have taken statistics courses will know that we often notice in the statistics about a system information about the association between different factors. So we want to try to understand what's going on. Or maybe we see something like the rising tuition rates across Canada. We see something about how a certain company had a very fast growth rate and has now plateaued. Or cases where we see high attrition rates, high dropout rates in an academic program. We want to know what's going on, what's driving this, what's causing this, why do we see this? And we'll often come up with these issues, especially if we're scientists. We want to understand, this is what I think is going on. Is this evidence consistent with it? If we want to know where's the situation likely to go next, maybe you've invested in Google and you want to know what's Google's stock likely to do over the next few years. You want to know what's likely to happen for it as Alphabet develops as a corporate initiative, but as they face crosswinds from Apple's competition, etc. You might want to know what's driving these patterns, and even what I'm seeing a good or bad indication. That may sound odd, but there are many times where the data that we're looking at, it may lead you to jump to a conclusion that it's good, but on retrospect, it could be a bad indication as well, or vice versa. An example of this would be, for those familiar with health issues, if we're dealing with something like cases of infection that are diagnosed in a population, we might see rising rates of these. We might see lots of reports and greater number of reports every year of this occurrence of this infection. But that could be a bad thing, and it's easy to interpret as bad. You know, people are getting worse and worse in terms of burden of infection. More and more people are getting infected. But it could be a good thing. It's just, there's a group of people out there who are more and more successful in discovering them. Maybe they were infected before, we just didn't report them. Now we're in fact finding them. And so now we can treat them or help provide medical care for them or help provide preventive services. So sometimes data that seems immediate in its implications is actually not, if you think about it. Whether it's data about corporate performance or data about burden of infection or what have you, there's often ambiguity there. The second big reason is we want to intervene. We want to change things. We want to make a computer cluster that's more performant. We want to design this computer system to be, higher throughput, to handle more requests per unit time. We may want to intervene in a healthcare system or in a health system more broadly, where we're focusing on certain groups that are at highest risk, maybe of getting infected by flu. High risk because they're more likely to get infected by flu, like they have weak immune systems, so they're in contact with lots of people. Or maybe high risk in the sense that if they got infected, it could be really bad for them. Or because it could be bad for others associated with them, such as a pregnant woman. How soon will I see effects? If I do intervene, how soon will I see? Okay, so suppose you're dealing with an executive of a company, and you're talking about launches of different product bundling strategies, and you want to know which of these strategies is likely to yield net positive cash flow within a year or two. Sometimes this is not so obvious. It takes time to roll them out. It takes time for customer uptake. There's customers who were with it before who leave, and you're not sure how soon you'll see positive effects, or how to scale up, or how to make a rollout financially sustainable. In short, when we have complex systems, ladies and gentlemen, we often have challenges in terms of dealing with them because they have counterintuitive behavior, or at least behavior that we didn't anticipate when we thought about the system. And this can lead to misperceptions. It can lead to cases where we're trying to make something happen and it blows back at us. It exhibits blowback or policy resistance, or where our effects have disproportionate impact. We cut back a little bit the funding for some preventive program, and gonorrhea explodes across Saskatoon. I know, you don't want to even think about it. And when we have these situations, it really poses problems. We need to learn from our experience. It's harder to do if we don't understand why we're seeing these things happening. To coordinate, if we want to have different actors coordinate with each other, to decide more effectively and to design a system, whether it's a computer system or a healthcare system that's more robust. Okay? So it's a bit of a review from last time of things that I was trying to communicate. And I argued that system science, complexity science as it's often called, is the science of the whole. It's about putting the pieces together and understanding how they contribute to the behavior of the whole, and how our changes at the level of the system at different points in the system will affect things. A lot of it, what it is focused on, is what we call counterfactuals. Anyone know what a counterfactual is? We talk about a counterfactual. What are we talking about?
Is it like a counterexample?
Not quite. It's a similar root, and in a way, it's a counterexample to the current situation. It's something that hasn't been observed before. It's something that's not currently the case, which we want to imagine. In short, in a very crude way, you could say it's a what-if sort of situation. We're asking, what if this happened? What if we were to do that? What if the University of Saskatchewan declared that it's tuition free. Yeah, I know. You can stop clapping. But you know, what would the implications be for student recruitment? What would it be for student quality? What would it be for student dropout? What would it be for the financial sustainability of the university? These are counterfactuals we could ask about. You know, what would happen if this was the case? And ladies and gentlemen, much of the world these days is focused, reasonably so, and very excited about the big data revolution. And in fact, we work very essentially in that. But one issue about collecting data and using it to inform our understanding is that we're counting on the situations that gave rise to the data being similar in the past to what it will be in the future. We don't have data yet about the future. And sometimes when things change, it changes the nature of the associations in that data. So for those of you who are from a little bit more statistical background, you will realize statistical tools work very critically with the methods you'll be learning in this class, but they are limited because we, as Kierkegaard said, we live forward but learn backwards. We learn from evidence that's from the past, and often we're simply hoping that elements of that evidence apply going forward. These sort of models are about asking about counterfactuals, things that have never been observed before. So we don't have data about it yet, about the outcomes or some aspects of the outcomes. So a central way in which system science makes use and tries to aid the science of the whole is through dynamic models. These models, I argued, are kind of a mechanistic depiction of a situation. We saw last time we could depict the stages of infection a person could go through. But it might be a depiction of the stages of handling of orders in a big firm like Amazon. Or it might be something to do instead with a mechanistic characterization of competition between firms. It might be a mechanistic description of how a computer network is tied in with a certain cluster, and you're characterizing the connectivity and the scheduling of jobs on these different computers. So these dynamic models are kind of a mechanistic depiction of how things work in the world. Now there's a star next to it, and we'll get to that star, an asterisk that indicates a qualification. But it's, roughly speaking, a simplified depiction of the world, okay? Or of our hypothesis about what's going on in the world. Occasionally we use them just as purely thinking tools, but often it's depicting a sort of at least a rough hypothesis about what we think might be applying at some level in the world. Now, why do we do this? I argued a couple of reasons last time. Number one, they help us share and reason about the system, reason consistently about it, concerning how things work. With a model, we can say, hey, run this thing in a much more reliable way than we can do with our head. That model that we had last time was extremely simple, but we would have been hard-pressed to say exactly how different values of parameters would have affected things if we had just depended on our head. It's by virtue of being able to run it that we could actually come up with an understanding of how the assumptions captured in that model have effects. Let me put it another way, if I could. Models sort of allow us to operationalize theory. They take theory out of our head and put it into a form that we can do useful things like run it and see what the results are, share it with others, get feedback on it, and refine it. Okay? They're learning tools, I argued last time. Learning tools that help us think more deeply, reliably, and consistently through a set of issues. And there's a point of view which is expressed most directly by Josh Epstein from my knowledge of the literature, where he argues, look, we don't truly understand a phenomenon until we can kind of generate it. We can without presupposing it, we can describe a system, the related system, and see it emerge from it, see it come out of that. We don't really understand otherwise why it's going on at a deep level, unless we can have this kind of mechanistic depiction. So simulation models can be viewed as kind of a dynamic hypothesis. Why dynamic? Well, it's a hypothesis how things interact over time in the world. It's dynamic. And the idea here is that in that model, we sort of say this is how things work. So we could ask what if. We could ask what if questions. What if things were different? Okay. So that's sort of some of the basics that we saw last time. And simulation models are far from any sort of guarantee that what's depicted is correct. But if there is a problem with what's depicted in that model, if it's inconsistent with the evidence, if it's inconsistent with observations by people who've worked with the system, we'll find those inconsistencies sooner. We'll locate the shortcomings of our understanding sooner if it's in a model and we can run it than we would if it had just stayed in our head. And I quoted Francis Bacon, although I didn't quote his Latin, in which he wrote, that said basically we learn sooner from error than from confusion. By trying something, putting it into a model, and simulating, we learn more quickly about the flaws in our reasoning by trying and failing in that way, or having it fail to match. We learn quicker than if we had just been in a vague sense in our head. Okay. So models help us provide a way of sort of asking, if we had this situation, what would the implication be for the whole model? And they can help us behave better with respect to those systems, make better decisions, ways of changing the structure of the system, ways of working together. Okay, so what are some uses of these models? Across all three types of models we'll see today, all three types, we are going to see certain commonalities. One commonality is the motivations that I talked about and the uses of these models. How do we use them in general terms? They differ in how much they tend to be used for certain types of questions for the different sorts. One is they make explicit our assumptions. They take it and they put it into a way that multiple people can look at, critique, refine, run it, etc. Secondly, they help us manage these systems by allowing us to ask what-if questions to evaluate what will happen if we change this aspect of the system. For example, if we had a mechanism of having an HIV vaccine, so we could prevent people from being susceptible by giving them a vaccine, how would that affect things? They can help us understand patterns empirically, data that we see, because we can compare it what's coming out of the model and say, is that consistent? If so, it lends some credence to my understanding of the system. Does my understanding of the system capture certain broad features? We can use it to prioritize data collection by testing sensitivity. It's one of the things will be of the model to certain assumptions. Run it with a higher value of this parameter and a lower value, see how much it differs. And it can differ remarkably between different parameters, different types of assumptions. And we can learn better from context by saying, okay, these certain ways of acting, are more effective in certain contexts or another. Finally, it can help with communication. Okay, so let's talk about the shared characteristics of these models. Okay, these models generally provide a description of a system and its behavior over time that where the behavior of the system is implicit with the model. Those rings that we saw last time, we did not specify those in the model. The fact that the susceptibles were outside of the infectives, that was not explicitly specified in the model. It emerged from the model in a way, but it was only implicit in the model specification. The model is going to be specifying the incremental changes. How, given the current situation in the model, how does it change over time? We saw that last time through those state charts, right? Do you remember that state chart we saw last time? What it said basically is, look, if you're in this state, you can go on to this other state after, well, there's some rule associated with it. Maybe it was after an exact amount of time, or maybe it was a certain chance per unit time. You have a 10% chance per day, a kick of the can every day to go over, something along those lines. So these models specify how things can change given your current situation. So given that you're currently infected, how can things change? Well, you can recover with a certain chance per day you're going to be recovering. But we're not specifying, we're not hardwiring into the model an assumption about how it behaves over time. That emerges from the model. The fact that this person and that person all are described with this and they're interconnected in these sorts of ways. Okay? System behavior is emergent. It emerges from the model rather than being something we pre-specify. Yeah. And it's behavior over time, but sometimes over space and other factors as well. We saw that last time, right? We saw those rings over space. Okay. These systems are generally nonlinear. When I talk about nonlinear here, I don't mean merely that they exhibit feedback, although that's true. They exhibit situations where one factor can ripple around a series of changes that either amplify or push back against that original factor. That is true. But what I'm saying about nonlinearity here, I'm talking about the behavior of the system is not merely a linear function of our assumptions. So if we double an assumption, it doesn't double the patterns of interest coming out of the model. Okay? And this nonlinearity, we'll be explicating it more. We'll be talking about it more as the semester goes on and pointing to very particular cases where it's located in our model and showing how it changes the model. But it has a couple implications. Number one, with nonlinear systems, you see counterintuitive behavior commonly. With a nonlinear system, you can't really reduce it to its parts, and that's where we get this sort of emergent behavior. It can't be reduced to its parts. It's not merely the sum of its behavior with respect to each part in isolation. That's part of being nonlinear. There's no specification of the behavior of the system over time that we can write down. We can't write down a nice formula for the rings that are coming out of it that will be that will characterize as we change parameter values how things will change. If we intervene in the system, we try to change something, we try to modify it, the results of that will be very different depending on the extent of that modification. And if we're undertaking different interventions, the effects of the sum of them, the combination of them may be very, very different from what we see in each in isolation, not merely the sum of it. It can exhibit what's called history dependence. Its behavior now is really shaped by where it's been in the past in many cases. And you can get lock-in behavior where it kind of goes into a mode and it just stays in that mode. It's hard to get out. Where did we see lock-in last time? Anyone remember? Where did we see it kind of go into a mode and just sit there?
When there were no more infected.
No more infected. So it was in this state for a while where it was getting infected and there were these rings and it was sort of spreading out and recurring, but then it could switch to a very different mode where it got locked into this pure susceptible state. Do you remember that? It was all yellow? Yeah. And we can also have sort of certain subgroups within the population, it turns out, depicted by a model be disproportionately infected. Okay, a couple more comments. Ladies and gentlemen, I like to use the analogy because it's a useful analogy, between models and maps. Look, any map you have of the world has a couple of characteristics it shares with a model. Number one, it is an abstraction of the world. What do I mean by an abstraction? Computer science is in many ways the science of abstraction. What do I mean by abstraction? Can anyone hazard a sort of rough understanding?
And gives you kind of a high-level overview.
I couldn't have said it better. It hides the details, and it's a generalization, or it handles many particular cases in a sort of high-level way. It can handle many particular cases. It hides a lot of details as key. And where do we use this in computer science? I mean, those from software engineering background, whether it's, I don't know how many of you have taken 370 or taken 214. A few of you may have had the misfortune of having my 371 or 470. But when do we use abstraction? Where do we hide details, like when we build software programs?
Modular code.
Yeah, we modular code. We separate the interface from the implementation. We talk about, we will provide a contract of sorts that says what this function does, but it hides the details of how it does it. And why do we do that? Number one, so people who use it don't have to worry about all those details. They don't have to be worried about exactly how it accomplishes it. Number two, to allow us as the implementers the flexibility to change it over time. So it's about hiding details. And models, ladies and gentlemen, hide a lot of details. They hide details that we don't think are terribly relevant to the phenomena we're interested in understanding or changing, and to allow us to think through the situation more simply, more clearly. And it's the capacity to omit these details makes models and maps feasible and useful. I mean, the fact that a map explicitly excludes a lot of types of information is really valuable. These days, you're using a lot of maps which are digital. You know, they have Google Maps on here, and we could zoom into it. But it's maybe an analogy that's more directly visceral when you have physical maps, right? If you had a physical map, time was, maybe folks have it now, that if you were in a car, you might have a map of Saskatoon there. And that map leaves out a huge amount of detail. Detail of some interest, right? Some interest for somebody, but not for driving. It leaves out detail about where the trees are exactly, and details about exactly the width of the sidewalk in different areas, even whether there is a sidewalk in place. Maybe how high and how low different areas are. The fact that there's a downwards gradient going across the University Bridge into downtown. These would be left out of an average street map. And because of that, we can focus on the things we really care about in the car, like how do we get from A to B on network of roads. On the other hand, what information a model leaves out, what information a map leaves out, depends on how it's going to be used. So if you were interested in knowing why brownouts are occurring in Saskatoon, why there's a loss of power, or why the water went out up in Atridge Drive, or if you wanted to know why there's flooding down on White Swan Drive, you'd be using a very different type of map from if you were trying to drive across the city. It would still hide details. It wouldn't show all the details, but it would show different details and hide other ones, right? Similarly, if you wanted to know something about making your way, what courses do you have to select within the computer science program to graduate in 3 years, maybe a high-level map of prerequisites and kind of dependency structure is what you want, like the map that they have down in the departmental office that kind of shows your way through the program. It's available online. On the other hand, if you wanted to know something about what skills you could learn as a budding software engineer, you'd want a different map. You'd want one that has a description for different courses, exactly what types of technologies you'd be using, or what sorts of types of programming you'd learn, etc. So models and maps are specific to purpose. Which details we leave out depend on how we're going to use them. And a model like a map is useful because we can use it in a more facile way, more lightweight way if we leave out a lot of detail. And you could say at some level that all maps are wrong. They're wrong. It's wrong. It's a wrong depiction of Saskatoon. And maybe that's true from a certain philosophical standpoint, but I would argue that it's probably not a very helpful sort of position to take at a practical level. It's actually the fact that a map is incomplete that allows it to confer value. And similar with models, the fact that they leave out information is key to derive value from. Among other things, we can build it in a finite time. If your models that you build for the projects, if they had to depict all the details of the situation inside out, you wouldn't get it built by the end of the semester. One of the biggest mistakes a modeling project can make is to try to describe the system in a full way. And I've heard that before. We're going to build a model of the immune system. Okay. Well, how deep are you going to go? You could characterize it at the level of individual atoms, or you could characterize it at the level of differential equations, at the level of stocks and flows. And if you just say we're going to model it, it leaves obscure, okay, what types of phenomena are you going to capture or not? Okay. Now, one of the catches here, so with models, we're leaving out detail. With models, what detail we leave out depends on how we're going to use them, what we're seeking to get out of the model. But with models, it's often more difficult to ascertain up front what we leave out and what we put in. And I argued that models are learning tools, and we learn over time what to put in. Okay. So a common concern for all of these models is going to be scope. What goes in and what goes out. But it's actually more textured than that. We distinguish with dynamic models between 3 types of things. and they're indicated here in parentheses. There are things that we just outright ignore, often consciously. We say we're going to leave that out of the model. There's other things that are shown in the model, but in a pre-specified way. Maybe it's a fixed assumption. Maybe it's a fixed number. We say, assume this. Assume the unemployment rate is going to be this. Or assume, the level of competition from other firms for the firm of interest is going to be such and such. Assume the market size is such and such. That would be an exogenous thing. We're saying, make this fixed assumption. It's fixed in the sense of being pre-specified. It's not necessarily fixed over time. So we might say, well, have it rise by 1% a year or something like that. Finally, and most centrally to the dynamic modeling enterprise, is the fact that some variables can be endogenous. What I mean by that is that by running the model generates them, it produces them, it computes them, it calculates them. You can use different words. The point is that it is running and outputting this sort of data. It's producing it. Now, what it's producing may be used by other elements of the model on an ongoing basis. It's not purely an output. It isn't purely epiphenomenal. It just goes out there and is not used. It's used as part of the model operation, but it's endogenous. So tell me, within that model we used last time, that little model of the spread of infection, that stylized space, what things, given that it depicted sort of a spread of infection, what things were, give me a few things were endogenous, a few things were calculated by that model.
The number of infected recovered.
Yeah, number of infected, recover, and susceptible. That's a great thing. So the model was generated. We didn't tell it what to assume there over time. It told us what resulted from that model, right? So there are these changing counts, in case you didn't notice it up top, number of people susceptible, infected, recovered up there. So the model generates these things for us. And in fact, it's not only the number. Number will be important. We're going to come back to that a lot in the next few lectures. But it's also which people were infected, right? Which one was red right now? Which one was yellow? Which particular person was in which state? That was all endogenously calculated. We weren't, other than infecting a single person up front, we weren't specifying that. By contrast, there are some things that are exogenous there, which we told the model and said, go assume this, make this assumption, and we told it to the model. The model tells us endogenous things. The exogenous things we tell the model. Give me a few things we told to that model. Maybe that differed between different scenarios.
Chances of infection.
Yeah, probability of infection given exposure. Another one?
How long the infection lasted.
How long the infection lasted. Excellent. So those are some good things. How long people stayed immune. How many people they were connected. Right? We had them connected to 8 people. One of mine, north, south, east, west, southeast, northwest, etc. So there were a lot of things we specified to that model in an exogenous way. Now you can imagine those things for a different model being endogenized. In other words, made as part of what the model produces. Maybe the probability of transmission to another, given a discordant contact, given a contact between an infected and a susceptible. Maybe that probability is not a fixed thing. Maybe it's something that changes. So if someone who's still susceptible is aware of lots of people around them who are infected, maybe they take more caution, and that probability goes down. Or maybe as the infection spreads, people have fewer neighbors because they engage in social distancing. They try to avoid hanging around in crowds, and the number of neighbors goes down. That would be if we were endogenizing some of those things. So we might do that if we wanted to evolve that model. But many of those things were exogenous. What things were ignored in that model? What things were left out? It just left them out.
The movement of people.
Movement of people, good. So some models of measles have people fleeing. I'm not sure how that realistic is for a measles outbreak. But you could imagine, something like a deadly infectious version of flu. Maybe people try to escape it. They try to hide from it. In fact, in the 1918 flu epidemic, where millions died in North America alone, and I think it was hundreds of millions across the world, there were at least dozens of millions, there were people trying to escape it. And in fact, in some of the recorded epidemics for other conditions, I think maybe yellow fever or what have you, you will find cases of fleeing. You will actually see with the, I think it was the yellow fever outbreak in Atlanta, yellow fever or scarlet fever, I forget. There were actually subsequent outbreaks right around the train line away from Atlanta as people sort of tried to flee, not knowing they themselves were infected. They infected other communities along the way. They infected others. So fleeing does go on. What's another thing that was ignored in that model?
Demographics of people?
Demographics, yeah. What sort of age are they? What groups do they like to hang around? And that might affect that connectivity a lot. So those are good. Those are good things. The point is that model, like all models, has to take some stance on these things. And it's not hard-coded in a fatal way into the model. It's just that for that version of the model, we made this division. Maybe we learn from it. We say, wow, this thing is really sensitive to our assumption about contact rate. And so we're going to start to think, what if we made contact rate endogenous? What if it depended on a person's perception of infection, how many people around them? How would that affect the model behavior? So we might modify it over time. But ladies and gentlemen, I would argue that for software programs, we see similar things. There are certain things the program is going to be producing, and certain things that are kind of fixed in the program, but they're represented. They're just represented in a fixed way. And then there's certain things which may be ignored, which are just left out of the program. Now, over time, we often change this modification, and representing more things endogenously, as calculated by the model, has some benefits in terms of representing things with greater flexibility. You can investigate types of things. Sometimes you can capture dynamics over time in a more accurate way, but it requires a lot more time and resources to build and to sort of tie the model down to actual evidence, to empirical data. And it can be more challenging to reason about. So when we add things in, we try to do so later as we've understood this set of things. That's when we make a step and add things in. We do not, and I said we do not, and with a double emphasis, build a model that up front has all sorts of pieces in it at once and then find ourselves mystified why it behaves the way it does. It's much easier to build it up step by step. Even though you think it's quite incomplete, you learn from it, and the model that results will be much more savvy. Come back to that point, okay? So we're going to talk about a couple types of modeling here, 3 types, and they happen to be the 3 types supported by any logic, okay? Great. So the first of them is system dynamics, okay? Maybe we'll try to spice this up with a bit of interactive components. So I would invite you, whilst I'm talking, to call up any logic, okay? And we'll do a little bit of exploration through some of the models built into any logic. Once bird, twice shy. Until we can thoroughly test Moodle and its ability to download these things on different browsers, we're not going to do that again. Turns out that part of the problem last time was people were using different browsers. Some people were seeing one thing, some people not. And I'm going to try to get to the root of that. But for now, we're going to go easy and use some built-in models of any logic. Okay, so what is system dynamics? Ladies and gentlemen, system dynamics is a way of reasoning about helping to manage, describe, and analyze feedback systems. These are systems where there's change. When a change occurs in the system, it can lead to a cascading series of changes that ripple around and either amplify or push back against the original change. A classic example of this, of a feedback, is hunger. Hunger, right? I grow hungry, and I'll undertake some actions over time which may lessen my hunger. I'll eat. Or I grow thirsty and I go take a drink of water. Those are examples of balancing feedbacks. There could be other types of feedbacks that are reinforcing. Cases where, like, if you see one infected person in that population, like we saw last time, it will infect others, which will lead to more of them, which infect others, and it's reinforcing. That's a feedback as well, viewed from the perspective of the aggregate model. So system dynamics is kind of a perspective, a feedback-oriented perspective of how to understand systems, as well as a methodology to describe them, reason about them, and to try to analyze them. Okay. We're going to see when any logic comes up here. Okay, minus loading. Please do your any logic so it'll be ready to use in just a minute with some example models. Okay, so system dynamics is a little bit unusual in the sense that I'm presenting because as a field, a literature, as a methodology, it tends to emphasize quite strongly not only quantitative components to kind of allow us to simulate a system at a quantitative level, at a numeric level. It also emphasizes qualitative depictions of a system. And often those are first stage towards quantitative characterization. Okay? And it's also distinguished by a focus on the modeling process, how we build models, not merely on the result that is built, the technical model. Okay? And partly because of that, it's had decades of attention to how you use models in the human theater of modeling, with people, so that you can build useful models that get used, as my colleague Jeff McDonald puts it. At the same time, it has this really rigorous mathematical foundation. How many people in this room have ever seen differential equations? Okay, I salute you. I salute you. You'll play to dig your teeth into here. System dynamics is built atop a foundation, mathematically, of ordinary differential equations. By ordinary, I mean it's variables with respect to time, derivative of variables with respect to time. And it helps. You don't have to work with the equations explicitly unless you want to, but if you understand something about differential equations, you'll get a lot more out of some of the mathematics of this, okay? And you'll understand rigorously why it's behaving a certain way. And there'll be some examples which will make a lot more sense to you folks about where they're running down that foundation. Because you have a range of analytic approaches you can use to do really neat things about how this model could behave over any values of the parameters, what are its possible modes of behavior. And then it has evolved software that permits you to sort of focus on what is described rather than details of exactly how it's simulated. So it's what we call declarative. Okay, so I've just called up any logic. And when any logic comes up, you to go to, like you to go to the example models area, okay? Now, this is likely to lead to the same splash screen here. Now, I'm going to make it full screen as I try to show. Okay, so here we go. Great. Come on, make it full screen. Okay, this is being truculent. Okay, great. So, ladies and gentlemen, in AnyLogic, there are dozens and dozens of example models. Some of those have come out of this lab. And I'd like to show you some that are based on system dynamics, okay? One of them would be this one called predator-prey. I'd like you to open it up. How did I get there? I went over here and I scrolled down in the example models, under this examples, down to predator-prey here, okay? Here we go. Yep. Okay, so this is loading the model. Did you folks find it? Okay, okay. It should be loading it into yours then too. And boom. Okay. Great. So logic, come on. Why is it so slow? Okay. Now within this model, I'd like you to go over to projects and double click on main. Okay. Go double click on main within the project area. And what you will see here is different from what we saw during our last session, okay? During our last session, what we saw in main was actually a depiction of a space in this agent. Okay, double click on model. Thank you. It's not called main. It's for those. That's fine. Okay, so I'm going to kill this. Boom, and now we should get better performance. Okay, so double click a model, and what you should see should be a model includes a depiction at a very high level, of the population. It should look something like this. Do you see it? Do you see it here? What we see here is as we say, two stock depiction. We have a population of hairs, and this counts the number of hairs, and this counts the number of links, okay, in the population. And these represent deaths of hares and births of hares, lengths of births, and there's some assumptions here. Mortality rate for lynxes, for example, and we're going to see something about that. So let's try this thing over. Let's try going and right-clicking on this and doing run, and we're going to see the consequence of this assumption. Okay, so here we go. Here we go, and here we're going to be running it, and what we're going to see here is under hares here, we see a decline in the number of hares over time, and it turns out that's also depicted down here in gray, and the number of lynx are depicted in red. Okay, over time, it's saying, okay, right now there's about 4,900. I'll pause it for a second. There's about 4,100 hares, 129 lynx, and over time, rate of deaths. So within the past year, there've been 5,172 hare deaths and about 5,200 hare births. Okay, and then lynx births, about 32 births in the past year and 37 lynx deaths. Now, we could run this, and we could speed it up. This little button will speed it up, and we can see that there's a certain dynamics elicited. This dynamics involve changing, fluctuating populations here, okay? Now, we could scroll up some of these parameter values, assume, for example, a higher level of hare births, and now we'll see correspondingly different patterns. We're assuming that hares have a higher birth rate. Alternatively, we might lower the number of hare births, and we will see populations that are more stable in their depictions. We could yank this up to a very high level, and we will see pronounced sort of variations in the sizes of the population as the number of hares rises and the number of lynx are competing with it is also fluctuating at much lower levels. So this is a system dynamics model. It's a model where we give values for stocks and we put in equations, or formulas, I should say, for each of these flows, okay? Hares times hare natality, for example, that gives how many hares are born in a given year, the rate of hare births in a given year. It's hares times some natality rate, some birth rate. Similarly, lynx births, there's lynx times lynx natality. So we put in assumptions for the flows, and the stocks are determined accordingly. The values of the number of lynx and the number of hares are derived based on this. So let's go back to the slides here. So as I say, this software is allowed to allow you to focus on what you're depicting. You describe this, it takes care of simulating, and you're describing these formulas that need to hold between the state of the system captured through these stocks and the rate of change in the system is captured through the flows, and it will play out the implications of it over time. So we're hiding a lot of the details of the how. Now behind this, it turns out, is differential equations, and we'll see how that unpacks in a few another lectures, probably another 5 or so lectures. Okay, a lot of the focus of system dynamics historically has been getting people to change how they think about the system, so there's a lot of focus on interaction with people, okay? A lot of focus on sort of using the models and learning from them. So a couple features of system dynamics that are notable. It focuses on feedbacks as shapers of behavior. Where's their feedback here? Well, ladies and gentlemen, we will see ultimately more hare deaths occurring. You can see it most directly with lynx. As the number of lynx go up, there's going to be a greater number of lynx deaths, greater rate of lynx deaths. A million lynxes running around in Saskatchewan will have a larger number of lynx dying per year than if we have 1,000 or than if we have 10. Okay? So as the number of lynx go up, the rate of lynx deaths rises, and that tends to bring down the number of lynx. It's a little bit like my thirst, right? I'm getting thirsty, take a drink of water, brings down my thirst. So it is here. Okay? So feedbacks are central to this approach, okay? And accumulations stocks. So this represents the number of lynx, and it's an accumulation over time of births minus deaths. And hares are an accumulation of births minus deaths for hares. So there's feedbacks here, ladies and gentlemen, and there's accumulations. And much of system dynamics focuses on understanding these. And it's a very rich type of analytic inquiry. These sort of models admit to formal reasoning. You can reason about them mathematically and reason about their possible behaviors as you change parameter values over wide ranges. Okay, and they can be applied at diverse levels of granularity. A lot of it is undertaken in a way with stakeholders, and a lot of it uses, of that work with stakeholders, uses mechanisms like this called causal loop diagrams that we'll be introducing within the next 2 lectures. Okay, these are semi-quantitative depictions. They're mostly qualitative, but they have polarity, which indicates the directionality of the link, which lets you reason about the system. Within these systems, stocks represent accumulations, and they capture the state of the system. They describe its current state. The number of hairs, the number of links specify the state here, okay, of the system. Okay, and flows are going to determine how those stocks evolve over time. So the hair population will be determined over time by the number of deaths of hares, the rate of deaths of hares, and the rate of births. Okay. So those are some elements of system dynamics. Flows dictate changes in stocks. As the inflow gets bigger and bigger than the outflow, the stock will go up. As the outflow is bigger than the inflow, the stock will go down. And stocks determine the value of flows. The number of links is here. Currently present determines the rate of link deaths, how many links die per year. And then that rate of deaths determines, in turn, how number of links will change over time. And one very nice feature of these models is that you can use them with analytic mechanisms that are very powerful very easily. So a couple notable strengths here before we go on to the other types of modeling. It allows us to capture continuous dynamics. Dynamics involving continuous quantities that are specified not in discrete numbers but in changes over time. It allows us to build a model very quickly. It supports sort of interaction with stakeholders. And you can basically specify what you want to see in a model in a quite declarative way with minimal programming. And for many people who use this, that's an attraction. Via formal analysis, you can reason more generally about model results, like how this the possible roads by which it could behave, and understand why we're seeing certain phenomena at a quantitative level, at an analytic level. That's very rich. And you can use it with machine learning mechanisms to do certain types of extra analysis. Okay. Next, we're going to talk about agent-based modeling. So I'd like you to close up this model, the predator-prey model. You'll find a number of others like it. And I would like you to go, again, back to that example. Load in a different example model. Okay. This example model is also going to be one, like the one last time, that's an agent-based model. And we're going to, in fact, look at the same basic area we just did, but from an agent-based perspective. It's called predator-prey agent-based. And I want to contrast that with the last one, which is predator-prey. This one is predator-prey agent-based. Same basic system, just depicted with different building blocks, different mechanism. Okay? Okay, ladies and gentlemen, I'd like you to load in predator-prey agent-based. The machine grinds. Then once it's loaded in, to go run it. Okay? You know load in for mine. Why in the world is mine so slow? So we're back. Okay. Here we go. Boom. There we go. Great. Okay, here we go. So we're going to run this model, and here we go. Now, but it's going to have a more fine-grained depiction, a depiction where there's going to be a representation of a greater number of exogenous factors, particularly particular animals. Okay, so here's a model, and what we're going to see here is lynxes on the one hand, on a spatial model, and hares also in the same space. And we're going to have hares and lynxes that are individuated. They're particular animals, and they are running around within the space with the lynxes pursuing the hares. They are going and hunting the hares. So a given lynx being in a given area will mean that it's going to be able to catch nearby. Oh man, okay, yeah. So we'll restart that. From is here what? What do we start to see coming out of this model that reminds us of what we saw in the last model? Anyway. Those are oscillations, ladies and gentlemen. Those are oscillations in the population. these oscillations don't look exactly like the last ones we saw. The last on that previous model, they were more mathematically, they were more pretty. They're more analytically appealing. They were more neat. Here we see actually fluctuations that are more jagged. Why is that, do you think? Based on our learning last time, why is it? What's one factor contributing to this?
Randomity.
Yeah. So we're going to have randomness affecting this in the way it wasn't in that other model. That other model was deterministic, meaning we run it once, we could run it once, we could run it 100 times. We always get the same results. This model, turns out, if we run at different times with different random number seeds, we'll see different things. But they're also somewhat different in their shape. It's not nearly as regular, but we do see these regularities coming out of it. Now, this is a model which has endogenized something that was not present in that previous model. That last model had hares and lynxes, and we had lynxes hunting the hares. What does this model have endogenized that model didn't? Sorry? So space? Oh, birth and death? Well, the other model did have births and deaths going on. They call it natality and mortality. It was just by a different name. What this model has is space, ladies and gentlemen. Not space as in the final frontier, but space as in there's an area depicted here which is explicit. And as I told you, lynxes hunt these hares nearby them. They're running after the ones nearby them. And that leads to a somewhat different dynamics. After all, there's boundaries and it's sort of hunting only locally. Whereas in the other model, a lynx could eat a hare, any of the hares. The hares were just in an undifferentiated group. Hares. It was just a count of hares. And it didn't pay attention to which hare was near which lynx. This one actually does. This one is a spatially explicit model. And as we'll see, spatially explicit models are fodder for really, really rich types of analysis. We're going to be looking at models that are spatial. We're going to be looking at several types, including models which have geographic information, so-called GIS models. They actually have the streets, ladies and gentlemen, of our fair hometown, Saskatoon, depicted in them. And you'll see people moving down those streets, or they can move down bike trails, as many of us do in the morning, or other features of the landscape. And we can reason about things in a spatial sense. So here we have a depiction that is different from last time. Let's go take a look at this. Okay. Now the theme here is quite simple. The lives of lynxes in the real world, ladies and gentlemen, are full of interesting texture. But lynxhood, lynxness, as captured in this model, is subject to particularly simple depiction. Can anyone characterize the life of a lynx in this model based on this? What sort of features do they have in their life? What sort of things occur in their life? Well, okay, hunt. Sometimes they're lucky and they eat. Sometimes they're not lucky and they go back to the state. And after a while, they die. Actually, they can't get food. Oh, what else can they do? Well, they can die. That's what this is. This is kind of the Death Star state. It's a final state which depicts the lynx dying, and they can also give birth and have babies. Okay, so it's a very simple, stylized depiction of a lynx. Let's go check out a hare's life. The life, ladies and gentlemen, of a hare is even simpler in its depiction. It's singularly monolithic. So basically, it's not a very encouraging life here. They can have babies too, but they can die because of age, or they can die because they got eaten by a lynx. Okay, it's a pretty sparse representation of this. But in both cases, and I didn't highlight it, but in both cases, lynx and hares, they have a associated with it, which is their current location. And if we were to go look at hunt, for example, here, they're going to be hunting after a certain period, and here they are going to actually go look for the the number of hairs around, and they will sort of get that hair, and then they will, if there's a hair around here, if they catch it, they will actually send the hair a message which says basically you've been eaten. Now this model is not made in the most transparent way, but the basic features of it are clear. This is the same basic structure, the same basic problem depicted, it's with different model assumptions, okay? And different endogenized features. This model has more features spatially than the other one. It also distinguishes each individual, okay? Over time, these individuals move. So here, this individual will go and move and jump to different cells around to try to sort of move around the space so they don't exhaust just the hairs in one space. We could go into this more. The point is, an agent-based characterization compared to a system dynamics characterization, okay? So with an agent-based model, we have a population of one or more populations of agents, and each of them is associated with some parameters, some assumptions that are more or less fixed, some state that changes over time, like whether they're alive or not at the most basic level, whether they're currently hunting, we could depict, it's actually depicted as an event here, and then some actions that by which they can change state, actions that might bring them from one state to another, like when they die, okay? And then rules for evolving that state, for changing that state over time. And then there's means of interaction with the states via an environment. So they're embedded in an environment and move around that environment. There's a time horizon we'll specify to the model and some initial state. Ladies and gentlemen, all of these models, we specify an initial state, and then we say, basically, how does the model change? Based on the current state, how does it change? What are the general rules for that? So we can play it out. Now, with a system dynamics model, ladies and gentlemen, we may remember we subdivided up populations. So we had lynxes and hares. Or if we had a population of people, like we did last time, we might divide up to susceptible, exposed, infective, recovered. Each of these counts the number of people who are in that state right now. Just like we counted the number of lynx, counted the number of hares at a given time. Here, we're subdividing up, say, a population into categories, and we're counting the number of each one. By contrast, in an agent-based model, ladies and gentlemen, we are dividing up a population into individuals, and for each individual, we are keeping track of their state. Let me see if I could put it this way, ladies and gentlemen. This is a very important point in this understanding the distinction between them. We saw two models, predator-prey, one agent-based, one system dynamics. In an agent-based and system dynamics modeling, we organize the model according to state. So we have a stock of hares, the state variable, lynxes, state variable of hares, and we count the number of each type, okay? If we add a population which could be susceptible, exposed, infective, recovered, we'd have a box for each. We'd organize the model by that. That would be kind of our structural units of the model. And then for each of these categories, we would keep track of the data that we would maintain, ladies and gentlemen, is the number that are in each of those stocks. Okay? The number who have that category, the number who are susceptible, the number who are infected, etc. System dynamics. We organize the model by state. We structure it by state is another way to put it. And we actually keep track of data that counts the number that are in a certain state. Agent-based modeling is like that, but turned on its side. The agent-based modeling, we organize the model by individual, by particular agents. And each agent has data that not count those agents. After all, there's one agent here. But they have data which tells for that particular agent what state are they in. What particular situation are they in right now? So on the one hand, we're organizing the model by state and counting the number that are in a given state. The other case, we're organizing the model by individual and simply for each individual keeping track of its characteristics. Okay? And we're going to see that agent-based modeling allows us to have nested models too, where you might have people and they're in a city or in a neighborhood, and neighborhood's in a city, and a city is in a region, and you can have this whole sort of hierarchy. Whereas it turns out that to capture that in a system dynamics model, you would simply have more stocks keeping track of the higher levels of aggregation. It wouldn't be nested. It would just be kind of flat, all in at one level. Okay, so here we have an agent population. We have an agent class that describes agenthood, or maybe more than one agent class, and then the simulation has many particular individuals. Each of those individuals has parameters, a particular value of those parameters. Maybe the agenthood, personhood, has 3 parameters. Each particular person in the population has specific values for these. And then each person has a state. So maybe they have these states or these possible states. Maybe they have multiple state charts. This specifies one set of concerns. This specifies another. Ladies and gentlemen, in software engineering, we talk about separation of concerns. It's a big impetus for my classes 371 and 470. We have the same need here. We separate out the concerns. These are the states with respect to care seeking, so like seeking care in a facility. These are the states with respect to infection. Okay, different types of states. And then they have a means of interaction. Maybe it's through a network, for example. Maybe it's through a space like this. They can infect each other by dropping some sort of pathogen in space, and it can infect another one. And we may see types of behavior like we saw last time that way. Okay. In contrast to system dynamics, agent-based models are typically stochastic. Okay, they exhibit randomness over time. That's what we mean by stochastics. It's not just it's randomness. We have a random number of people in the population. We actually have randomness over time. Who goes to what? And that's mostly because they're very fine-grained. They depict things that are reasonably hard to deterministically set or to determine. And as a result, we run these models many times to get secure understanding of the results. We don't let our results just be the fluke of one run. We run it several times over. And this can actually be a real asset. It takes more work, but it can allow us to explain variation we see in the real system. So in these models, do you remember last time we went to simulation, we went to the experiments, we scrolled down, and we saw that we could change it from a fixed seed to a random seed, and that changed the particulars of the run every time. So we may have a particular run yields a particular precise set of outputs, but by running it many times, we have different outputs for different runs. And by running it 100 times or 1,000 times, we see distributions in results for different scenarios. Okay? I think I'm going to stop here to allow people to leave. We will continue this discussion in our next class and just finish up discrete event modeling, which will be very quick. In the meantime, please see if you could load in and examine one final so we get into the next subject. There's a model there which is called Trauma Center, okay? And it may have been renamed in the last one, so Trauma Center, this one right here, okay? Trauma Center. That will be your example discrete event model. It depicts in a hospital, and the hospital has arrivals from ambulances and arrivals from walk-ins, and it shows how the people flow through the hospital, how they're dealt with by nurses and doctors and so on, and how they're discharged. So see if you can go open that up, see it run, and I will see you during the next class. Hi. Sure. Yeah.